Alright, so today we're going to be looking at ethane, which can be written as C2H6, which means it has 2 carbon atoms, 6 hydrogen atoms. So, ethane is normally a colorless, odorless gas used for combustion, found at standard temperature and pressure. It does all kinds of cool stuff, but we're going to look at what it looks like structure-wise and give it a little bit more of an idea. So let's find carbon and hydrogen on our periodic table, and we'll go from there. We have carbon over here in the corner. It has 4 valence electrons in its outer shell because it's in group number 4, right here. So, group 4 has 4 valence electrons in its outermost shell. That doesn't mean that it has 4 electrons total, just in the outer shell. Then we're going to come over here and find hydrogen. Hydrogen has 1 electron total, so it only has 1 electron in its valence shell. It is an energy level 1. Energy level 1 can only have a maximum of 2 electrons anyway. 2 is for helium, 1 is for hydrogen. So we're going to put that there. Now the second energy level, right here, can have a total of 1, 2, 3, 4, 5, 6, 7, and 8. 8 electron totals in that second energy level. It only has 4, so it could use some, or it could give away some, either or. We'll start off with hydrogen though, give this an idea. So hydrogen it could use 2 to fill that shell, but it only has 1. So that leaves us with 1 left over. We could use 1 electron to fill it. Then we have carbon, which could use 8 to fill the shell. It only has 4. So that leaves us with 4 left over. We don't really know why that matters yet, but let's find out. Something called valency. So valency is basically the number of bonds that an atom can make in order to fill the shell, the maximum number of bonds. So, for example, hydrogen can have 1 bond total. It needs 1 extra electron, so it means it can make 1 bond to fill that shell, and it'll be happy. And then we come to something called the octet rule. Octet rule doesn't apply to hydrogen because it only has 2 electron slots anyway in that whole shell. Now, for the second energy level, we come to the octet rule. Octet rule basically states that an atom will do just about anything to give away, take, or share electrons in order to get that full 8 electrons in its outer shell. So, carbon has 4 electrons. It needs 8. So that means it can use 4 electrons, which means it can make up to 4 different bonds. 4 separate bonds in order to fill that shell. That gives us our valency number. So the valency of hydrogen is 1, and the valency of carbon is 4. Pretty straightforward. So let's look at our electron configurations. Electron configurations are important. They give us a basic idea of the structure of the electrons around the atom. So let's go back to our chart here. So we have our S block, P block, which is this right here, and we won't worry about D for right now, or F. But anyways, so carbon is obviously the larger of the 2 atoms. It has more electrons, which means it needs more space in general. And then it also has like 10-fold the mass. So it's obviously the bigger of the 2. It's going to win that arm wrestling match. So in order to make our electron configurations, we're going to use our energy levels right here and our blocks, along with how many electrons we have in each of those blocks, which are also the orbitals. So we're going to come way back over here. Let's start off with hydrogen. So hydrogen has just the 1 electron. So we're going to start off with that first energy level in the s orbital, the s block, s orbital. It only has the 1 electron. So it's 1s1. Ta-da! that is the valence electron configuration for hydrogen. The easiest one in the world. Then we're going to come down to carbon. It's a little bit more complicated, but it's really not. So we're going to start off, we got to go through the first energy level to get to the second. So, first energy level, s orbital, it fills that second s orbital. So then we're going to go to the second energy level, which is 2, which is basically our new shell. We filled the first shell, we're going to go to the second shell. And we're going to go to the s orbitals, and it's going to fill both of those. Swirl over real quick. Fills both of these. Well, now we have to fill these two. So that's 2, and at the potential 1, 2, 3, 4, 5, 6 possible slots for it to fill. So we're in the p orbitals. So we're going to go second energy level, p orbitals. It only has 2 electrons, so we're going to have 2. So in the outermost energy level, which is the second energy level, it has 4 electrons. The valence electron shell, or the valence shell, contains 4 valence electrons for carbon. And that's all there is to it for that. It's quite simple. Alrighty. So now we're going to leave that. We're going to go to something called electronegativity. So electronegativity is basically the atom's attractiveness for electrons, or how much it wants its pull on electrons. The greater the electronegativity, the greater the pull it is on electrons that are nearby it. So that is important for bonds, like covalent bonds, where electrons are shared. So one atom might pull on that electron more than the other, giving it a slightly more negative charge than the one that's pulling from, giving that a more positive charge, which would make that bond polar. So we'll come back to that in a second. So we find carbon right over here in the corner has a electronegativity of 2.5. We have hydrogen over here has an electronegativity of 2.1. You subtract the difference from that, we get an electronegativity difference of 0.4. So that's right at that threshold. That would make this a polar bond. Anything under 0.4 is going to be pretty much a pure covalent bond. For example, a bond between 2 carbons would be pure because there's no difference in electronegativity. There's no pull greater to one side or the other. It's split even. They have equal custody of that electron. Now, for example, the hydrogen and the carbon being more electronegative is going to pull on that electron slightly more than that hydrogen, making it the smallest polar covalent bond. Alrighty, so now that we understand that, let's apply that a little bit. And we're going to look at Lewis dot structures. Sorry about the screen being all over the place. Alright, so let's look at Lewis dot structures. For Lewis dot structures, first thing we want to do is figure out how many valence electrons we have in total. We're looking at C2H6. Now carbon has a total of 4 valence electrons, but we have 2 carbons, so we're going to multiply that by 2, which gives us 8. We have hydrogen. So hydrogen has valence electrons of 1. We have 6 of them. So that's going to be 6. We're going to add those 2 together. So that gives us a total of 14 valence electrons. That's going to be quite helpful when we're making our Lewis dot structure. It helps us double check and gives us the basic idea of where we should be placing extra lone pairs and stuff like that, if there is any. So first thing we're going to do is make a little skeleton of what C2H6 would look like. So we'll draw the carbon with another carbon. Alrighty, so that looks pretty straightforward. It's nice and symmetrical. We can split it right down the middle. What happens on one side happens on the other, and that's good. The electrons like symmetry. They like to be as far apart from each other as possible. So we have 14 valence electrons. Let's see if this actually makes sense. So for each of these lines, it means that there's a covalent bond. So for each covalent bond, there's 2 electrons. So we're going to go ahead and put one there for each hydrogen. And then let's give each of our carbons their electrons. So like carbons have 4 electrons, so we're going to put one on each side. Alright, so this makes how many electrons? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 electrons there. We have 14 electrons here. That is perfect. It doesn't get much simpler than that. So we have 14 electrons, valence electrons, in this Lewis dot structure. They are all perfectly paired and ready to go. Now, I did these in different colors for a reason. So remember when we talked about the polar covalent bonds? Well, the carbon has a slightly more negative pull, stronger pull on those electrons than the hydrogen does, which makes the hydrogen slightly positive. So each of these hydrogens is going to be slightly positive. And then each of the carbons are going to be slightly negative. So that makes more sense. Everything's kind of pulling towards the center, which is kind of how you want it to be for a nice strong bond. And then these 2 carbons right here in the middle form that beautiful pure covalent bond with no difference between them. So in reality, that could be drawn as, oh no, I deleted the carbon. Carbon delete? Looks like that. Now you can rewrite that to the basic structure of without all these dots. Let's see if I can do this. Oh no. Okay. So for each of these covalent bonds, ta-da! There we go. There's our basic Lewis dot structure. Alright, so we're going to skip the whole 2D space thing that we were just working on. We're going to go to 3D. So let's look at some cool stuff. 3D geometrical structures. Because in reality, they're not perfectly flat like that. So we have our carbons, the same general structure. And then we're going to have the 6 hydrogens, but instead of them being completely symmetrical like that, they're going to be a little bit curved because we want them to be as far away from each other as possible. Because in reality, they don't want to be close to each other at all. So they're going to have equal distance between all of them. I'm going to switch to a different color. Oh, I thought that was a different color. Alright, let's switch that. So we're going to have 1 hydrogen up here. Then we're going to do 1 hydrogen kind of going out into space. Kind of going behind the atom. And that's what these little lines represent here. And then we're going to have 1 hydrogen kind of coming towards us. That's what that thick, filled in, triangle looking thing looks like. And that's what it represents. We're going to do that on both sides, make it symmetrical. 1 going out into space. And 1 right up here in our 2D plane. Alright, so we have the 1 coming at us, 1 going away from us, and the 1 that's kind of just sitting there in between in its flat space, its 2D space. And that is the 3D structure of the ethane molecule. Now, we get to something called resonance. And resonance is, that's a weird plural, resonances, but resonance is kind of like the theoretical, what if there was a double bond on one side, but it could have been placed on this side, and it really doesn't do much of a difference whether you place it on one side or the other, but we know that it could be on either, so neither is true. So they came up with this kind of hybrid theory called resonance hybrid. Basically, they draw 1 model with the bond on this side, and 1 model with the bond on this side, draw an arrow in between. And that means that it's kind of like a blend of the 2 models, but we don't have that with ours. And then we have what's called formal charges. And that kind of relates to the polarity of what we did over here with our Lewis dot structure. So the formal charge carbon if it has 4 electrons in its base atom. And then it forms 4 different bonds over here. So we're going to take half of those electrons from those 4 bonds. So minus the 4 gives us 0. So the formal charge of carbon in that is 0. And then the hydrogen starts off with just 1, and then it only forms the 1 bond per carbon-hydrogen bond. And we're going to take half of those electrons, so that leaves us with 1. It comes out to be 0. So the formal charge between both of them equals 0, which just makes sense because the formal charge of C2H6 is 0. And that's pretty much formal charges in a nutshell. And that is ethane in a nutshell. Hopefully you liked this video, and maybe I'll do it again one day. We'll see. But have a great day.